Okay, in some cases, we have to be a little bit more creative in rewriting our expressions than in others. And this is one of those cases right here. Uh, we don't exactly have one of the forms that we need, but it would be nice if we could rewrite it into a form that's useful. In this case, it looks kind of like we're looking for an arctangent sort of expression, right? Recall if we had the format where we had du over something like a squared plus u squared, or u squared plus a squared, it really doesn't matter which order we put in that, we would be getting an arctangent function, 1 over a. Let me rewrite this a little bit right here. We would be getting the format 1 over a arctangent of u over a plus c, right? And it looks kind of like that we could do that right here. Problem is, of course, we've got this extra term, negative 6x, so what do we do? Well, the answer in this case is that we're going to rewrite by using the method of completing the square. Now, if you don't remember that, we have an expression that looks kind of like it could be a perfect square, except it's a little bit off, right? A perfect square is the kind of expression where if we had x squared minus 6x, right? If the leading coefficient is 1, we could take half of the middle coefficient and get that squared at the end and have a perfect square, which is to say plus 9, right? And it'd be nice if we could have a plus 9, but do we have that? Well, we're really, really close, aren't we? Right? Plus 10, well, if I just added a plus 1, I would have the equivalent expression right away, right? So look at this denominator right here. I've got x squared minus 6x plus 9 plus 1 already in place. That's a useful thing. Okay? Now, I've rewritten it down here in the denominator so that you can see, yeah, look, x squared minus 6x plus 9, how does that factor? Well, that factors this way, dx divided by x minus 3 squared, being one of our special factorization forms, right? X minus 3 squared plus 1 dx, and we might notice this looks an awful lot like this expression right here. The only difference now is that we might try to say, well, let's let u equal x minus 3. What's going to happen? Well, sure enough, du is going to equal 1 times dx. So we're practically already there, right? Look at what we've got now. We've got du divided by u squared plus 1. Well, sure enough, that is, as we said, 1 over a. Well, a in this case is equal to 1, so it's going to be 1 times the arctangent of u over 1 plus c. So if we make our replacement, sure enough, here's our antiderivative arctangent of the quantity x minus 3 plus c. And so very often, if we run into one of these kinds of expressions, this is going to be a useful tool for us. We're going to complete the square if we run into something that is of the form dx divided by ax squared plus bx plus c, right? When we see this sort of format, we're going to complete the square and use the format for our arctangent function to take the antiderivative. Right? So that's the plan right here. Let's see what we can do with that in class.